Hey everyone, hope that you're having a great day. Today we're going to do a little intro to motion, and we're going to be focused on motion in 2 dimensions. In BC Calculus we do 3-dimensional motion, but we won't do that until later on in the second semester. So today we're just going to be able to relate position, velocity, and acceleration using derivatives through graphs and using calculus. Let's see what we got. So some of the vocabulary we're going to talk about: position function, the velocity, direction, speed, acceleration, displacement, and distance traveled. And you might say, this sounds a lot like physics. Well, it really is. Everything that you do in physics relies on math, and being able to use your calculus to get these concepts and how these different functions relate is very important to the development of calculus, and that leads into physics. All right, let's take a look. So you have these lovely handouts, and we're just going to run through the notes. I'm going to kind of take you through what I want to have in each of these boxes, and this is kind of a quick reference to come back to anytime you have any questions about motion, and then I'm going to kind of take you through how I approach motion problems and how I try to tackle these things. So first of all, we're going to talk about the position function. So the position function often is used as x of t or y of t, or sometimes they use s for the position. And if it's x of t, sometimes they'll say, you know, there is a particle moving along the x-axis. So I think about a particle as a dot. So that means it's moving left and right along the x-axis. This is why it's 2-dimensional motion. It's not moving up and down. In addition, it's just moving left and right. If it's y of t, then it's probably moving up and down. So you have your particle right here moving up and down. Okay, and then s can be just a generic position function. So what it tells you is where the particle is, in relation to 0. So for example, if we're on the x-axis, if I tell you that x of t is equal to 5, that means that you're 5 units right of 0, right? So the particle will be right there. If it's negative 3, it tells you you're on the left. So negative is below 0, and positive is above 0. Okay, so it tells you if you're up or down or left or right. It just tells you where the particle is. That's the only thing it tells you. So units often for this are just units. So you can say 5 units. Meters is pretty common, especially in physics. You might have feet, miles, etc. So this kind of stuff, right? So it's units, like the base core of units, kilometers. I don't know, furlongs, if you want to do that, sure. So just kind of anything that measures distance. The velocity tells you where the particle is going. So v of t, or the reason that we can use derivatives is because think about position. So if you were to graph position as a function of time, and I'm actually going to throw this in here. We're going to do this with each one of these. So if the position graph looked like this, let's say the position graph looked like this. Okay, we're going to graph the same graph for each one. So this is a position. Let's say you're on the x-axis, since I've got the x still drawn up here. So this is x of t, and this is t. So this tells you where the particle is. So the particle starts at 0. That's right here. Then it looks like the particle starts going positive. Let's say this is like 4. Okay, so the particle is going to the right, right? That's what's happening as it climbs here. And then it gets to 4. And then what happens from here to here? It stops. It doesn't move, right? It just sits there because it's at 4 that entire time. And then we start to go back. Right? At this point, we hit 0 again, and then we continue in the negative direction, and then it turns around here and comes back, and it stops at 0. Okay, so that's what we would have position versus time graph. Now, let's say this is like feet. So feet versus time. So if we go 4 feet to the right, we stop for a while, we go back negative a little bit, and then we come back to 0. So if you look at the slope of the line, change in y over change in x, or in change in position this time, and divided by time. So that would give you feet per, let's say this is seconds. Well, feet per second sounds a lot like a velocity. The slope of the position graph is equal to velocity, right? So this is the slope of the position graph. Okay, slope of the position graph. And so that's why we can use the derivative of the position function to give us velocity. So what it tells you is the magnitude and direction of motion. Okay, so if velocity is positive, it means you're moving right. If velocity is negative, it means you're moving left. Okay, this is important. So if I draw my x-axis again, here's 0. So if we're moving to the right, it's positive. If we're moving to the left, it's negative. If you were going up and down, like on a y-axis, then up would be positive, down would be negative. Okay, so if velocity is negative 5 feet per second, that means you're moving left or down at 5 feet per second. Okay, so units per second, common, meters per second. You might see miles per hour, feet per minute, something like that. Feet per minute would be pretty slow, but yeah, that kind of stuff. So it's going to be a unit divided by a time. That's all you're looking for. Okay, so velocity is telling us the change in position, which is why it makes sense that the slope of the position function or the derivative of the position function gives us velocity. So if we draw that same graph, but we pretend this time it's the velocity function, this means something very different. So I'm going to draw the same graph, and we're going to talk about what it means if it's velocity. Okay? So if this is v of t, and this is t. So this is now graphing how fast we're going. So initially, we're not moving at all. Whenever you're at 0, we call that at rest, because it's not moving. If the velocity is 0, you're not moving left or right at all. So that happens at 3 times on this graph. So at 3 times, the thing is not moving at all. So we start from not moving. Now, we start going faster and faster and faster. This time, what does the straight line mean? That means we're going 4, let's say it's feet per second, that entire time. That entire time from here to here, we're going at 4 feet per second in the forward direction. So we're actually moving forward that entire time. This is where people get confused. At this moment, we're still moving forward, right? Because it's a positive velocity value. On the position graph, that meant we were going backwards. But on the velocity graph, it's still a positive value, so we're still moving forward. Still moving forward, but we're slowing down, right? At this point, we stop. So what actually happens there? Well, we were moving forward, now we stopped, now we're moving backwards. We turned around. So if you think about the x-axis, we're going forward at 4 feet per second a long time. Now we're slowing down. We stop, and now we're moving to the left. So we move left a little bit, and then we are moving faster to the left, and then we slow down, and then we stop at the very end. So in this case, if we started at 0, we would actually end up quite a ways to the right, because we were only moving left for a little bit, right? Kind of interesting to think about. All right, speed. Speed is just the magnitude of the motion, so it's magnitude only. So this basically ignores direction. So this is just the magnitude only of motion. So this is like 55 miles per hour. I don't care if I'm going forwards or backwards, doesn't matter. If you ever have a cop stop you, you can kind of use this idea. You could be like, well, my velocity was negative, officer. I'm going home. So clearly I was under the speed limit. Probably don't do that. You'll probably get a ticket. But anyway, the units are the same as what we had for velocity. Let's check out acceleration. So acceleration is the second derivative of position, or you can use the derivative of velocity. So it's telling us how velocity is changing. And that makes sense to me because, like before, this whole time we're accelerating, right? We start from a velocity of 0. Eventually we get to 4 feet per second. And the question is, how long did that take? Well, if it takes 3 seconds, then we ended up at 4 feet per second over 3 seconds. So we're going 4 feet per second divided by 3 seconds, which is 4/3 feet per second each second. So each second we gain 4/3 feet per second, or you can write that as feet per second squared. Okay, so derivative of velocity, which means we can just take the second derivative of the position function. Okay, so second derivative position function or the first derivative of velocity. So this is the change in velocity. Okay, change in velocity. Now, this is an important thing. If v of t and a of t have the same sign, then the particle is speeding up. Okay, this makes sense to me because in the forward direction is the easy one to do. If I'm on the x-axis and I'm moving forward, so that's my velocity, that tells me I'm moving forward, and my acceleration is also forward. So if I'm moving right and I'm accelerating right, I should be speeding up in the rightward direction. The weird thing is, if I'm going left and I'm accelerating left, so this would be v of t is less than 0, over here positive, and a of t is also less than 0, I'm also accelerating. I'm just doing it backwards. So if my velocity is like negative 5 feet per second, and my acceleration is like negative 1 foot per second, then that means I'm going 1 foot per second faster to the left every second. Kind of cool. Okay, so same signs speeding up. If they're different, it's slowing down. Slowing down. So that would mean like I'm moving forward, but I'm accelerating backwards. I always think about this as like there's a rubber band pulling you back. I could be moving forward, but slowing down, right? I could also be moving backward, but slowing down, which is weird because the acceleration will be moving me forward. We'll do a lot of problems with this speeding up and slowing down. We'll talk a lot about it. So units per second squared is kind of what we're going to be looking at for acceleration. Meters per second squared, feet per minute squared, maybe miles per hour squared, all this kind of stuff. Yep. All right, displacement. Displacement tells you how far you've moved. So if here's 0 and here's 1, let's say. If I move here, and then here, and then here, and then here, and then here, and I stop right here, my displacement is only 1. Even though I've done all that moving, displacement just tells me the change in distance. So this is the distance that you've moved from the starting point. Distance from the start. That's all there is to it. Meters, feet, miles, that kind of stuff. Okay. Total distance traveled means you have to add up all of the absolute values of the change in position. So in this case, you would have to do, okay, I went forward for a while, so I'm going to take that. I'll add that to the distance I move back, add the distance I move forward, add the distance I move back, forward. You're adding all of those pieces together. Okay, so this is the total distance traveled over a time interval. And use the same units. That's all there is to it. All right, so I want to show you just a couple little tricks that come with motion. So first of all, I create what I call the tower of functions. Okay, so the tower of functions, basically all you do is you have a position function. This is the first time you'll see the tower. You'll see me do it a lot this year. And all you're doing here is as you go down, you take derivatives. So s prime of t gives you v, v prime of t gives you a. And remember, this is position, velocity, and acceleration. Okay. So another way to say v of t is s prime. I got it over here too, but this is v prime, which is also s double prime of t. Okay. The position just tells you location. The velocity tells you direction and magnitude. You may have seen The Incredibles. No, not The Incredibles. Despicable Me. Despicable Me, you have Vector. He is fighting or creating crime. I don't remember what he says. Magnitude and direction. Funny guy. All right. And then the acceleration tells you how v is changing. Now, if you have a graph, let's say this is a velocity graph. This is a trick for speeding up and slowing down. We'll do the one that we had before. Okay, so speeding up and slowing down. This little graph trick, it works really well if you have the velocity graph only. Okay, this only works for a velocity graph. So we're going to talk about speeding up or slowing down. Let's kind of talk about it. So here we're at rest. Here we're also at rest. That's very brief, right? We're turning around, and here we're at rest as well. So if you start from rest, this first time, I think you would agree with me that we're speeding up, right? We're going from 0 to 4 miles per hour. Let's say this is miles per hour. Okay, so this entire time we're speeding up. And then we aren't changing at all, right? We have a constant velocity at 4 miles per hour. So we're moving at a constant 4 miles per hour that entire time. Right, it's pretty boring. Let's make it 40. 40 miles per hour. Okay, and then, would you agree with me here we're slowing down? Right, we're going from 40 miles per hour down to 0. We turn around, then we go backwards. So at this point, let's say that we're at like, I don't know, negative 30 miles per hour. Okay, so at this point we're at negative 30. And then we slow back down to stopped. So basically what happens is anytime the graph is going away from 0, we are speeding up. Anytime it's getting closer, we're slowing down. That's easy on the positive side. The negative one is the one that confuses people. At this moment right here, we're moving backwards, but we're actually getting faster in the backwards direction, because here we're not moving at all. And then at this point, we end up going at negative 30. So we must be speeding up. So this time right here, because the graph is going further away, we're speeding up. And then right here, we're slowing down. Usually this is what AP asks questions about, is when the graph is going uphill, but it's below the x-axis. They say, are you speeding up or slowing down? And everyone's like, oh, it's moving up. You must be speeding up. No, you're moving closer to the 0 line. Anytime that your velocity is moving closer to the 0 line from the top or from the bottom, you're slowing down. So I just wanted to show you that little trick. We'll use that a lot this year. And that's all I've got for you for a little motion intro here. Love you guys. Hope that you have a fantastic day.